right. Well, welcome, welcome, welcome. It is Coffee Break with Microchip, where we take a few minutes out of your day to talk about trending topics or ideas of interest, hopefully topics or ideas that are useful to you in your design endeavors. So welcome back. Hope everybody's got their beverage ready to go. We are ready to go here. Today's topic is power meters, power monitoring. And joining me here in the studio to talk about it is Mitch Polonsky, Senior Marketing Manager in our Mixed Signal Products Group. So Mitch, welcome.
Thank you. Thank you, Ross.
Nice to have, as always, nice to have people in the audience or people in the studio with me. So we'll get going in just a second, but as always, before we get started, we will go to Austin in the booth. Austin is monitoring the interwebs for comments and communication. So Austin, welcome, and can you tell folks how to get in touch with us?
Absolutely. Thank you, Ross. Good morning, Mitch, and to our audience. I am looking forward to monitoring today's conversation, and as usual, we are currently broadcasting live on LinkedIn, Facebook, and YouTube. Also, our experts are standing by in the chat to respond to your questions in real time. And if you prefer to submit your questions via email, you may do so at livestream@microchip.com. Once again, that's livestream@microchip.com. And don't forget to please like and subscribe here to our YouTube channel as well as our LinkedIn to be the first to know about all things Microchip and Coffee Break. Back to you, Ross.
Thank you, thank you. So Mitch, power. Power is obviously a critical component of every design. And monitoring, measuring power throughout that system is both important and can be a challenge. So can you talk a little bit about what that challenge looks like and what we have today to share with the audience?
Sure. So what we're going to start with is we're going to go over our latest precision power monitors. It's also nice to go over a little bit of nomenclature because power monitors are also known as current monitors. They're also known as high side current sensors and current sensors, right? So for the engineers in the audience, you know, we are talking about all of those devices, but more specifically, the power monitors are a device, an IC, that sits across a sense resistor. And so functionally what that device will do is that it will measure current, voltage, and power. It can be connected to a higher voltage rail, which is nice. It helps with bill of materials cost reduction. You don't need as many protection devices. And in the case of the PAC1944 and 5X, our newest family, it can measure 0 to 32 volts, or in the case with the 4X, 0 to 9 volts. But lastly, these power monitors will report their values over a communications bus, in this case, I2C or SM bus. But Ross, you asked about, you know, the power monitoring challenges, and so what that would bring us to is that one of the challenges associated with power monitoring is the fact that a downside to power monitoring is I have to consume power to measure power. And so that's the downside to power monitoring. And a single power monitor can consume up to 360 microamps or more in a system. But what I want to impart to the audience here today is how the multi-channel power monitors actually really bring a benefit of a lower system power consumption to the equation of how much power consumption is going to go on. So, for instance, with a multi-channel power monitor, let's take the 2-channel power monitor, the PAC1952, for instance, we can measure or save ourselves, let's say, 31% of the system power compared to reuse of those single power monitor devices sprinkled across your board, right? So with more channels, I actually even get more savings, more power savings, and these families will measure 1, 2, 3, 4 voltage rails.
So you not only save power, though, you also save board space and layout and all that other nastiness that goes with it when you've got multiple power monitors all over the board.
Exactly, exactly.
All right, and at the beginning you mentioned about the ability of this particular part to report out data.
Right.
Can you talk a little bit about why that's important?
Yeah, definitely. And so what's nice about this family of devices, these two families of devices, are that there are two alert outputs that can be used to define, capture, warn, and alert to the system. And you can divide and conquer as a system designer with those two alert outputs. For example, maybe I want to capture the spurious current events separately from the spurious voltage events. I could set alerts in alignment with those goals. Not only that, I can measure or mask whichever voltage rail I'd like, and so that makes everything nice and easy to do that dividing and conquering for my system warning and event detection.
Great. So, as I kind of alluded to at the beginning, I think that that power and measuring power and designing power systems can be as much of an art as it is a science. Okay, it's there's a lot of techniques. What do we offer designers with regard to help support tools to help them implement these kinds of designs?
Right, right. Great question. Right. So I think that we were conscious of some of the challenges for the system designer, and so specifically we wanted to make sure that these devices were able to save time to market as well as simplify the characterization associated with prototyping. So at the onset we made sure that with this wide dynamic range of measurement, with the same voltage rail that I'm monitoring, I can measure low power consumption events, maybe trickle charging, and high power consumption events, maybe battery charging, with the same voltage rail. And I get that with 16 bits of resolution in these PAC1944 and 5X families. Not only that, we included a lot of driver support, right? So we have MPLAB-X, we have the Python code, we have Windows 10 and 11, actually, 11 being the latest, drivers available, and we have Linux drivers on the way. But also, what's nice about these devices is we will calculate the power on chip to lower some of the code overhead, right? So we are measuring voltage, measuring current, and we are multiplying the two together to give a product already digitally available to the designer. Lastly, for prototyping though, I would highlight the fact that we've added a burst mode measurement. And so what burst mode gives us, which may be familiar to a lot of the designers out there, is I can take one of the multiple rails and I can increase the speed of measurement or sampling on that one voltage rail, and I can use that for better characterization and prototyping. So,
awesome.
Yeah.
So that's a great overview. Now let's sort of go back a step or back into it.
Right.
And let's talk about the PAC1944X and the part specifically, and some of the applications and some of the features of that make it good for those kinds of applications.
Okay, great question, Ross. So we chose to design the PAC1944X specifically for lower voltage rail applications. And we really think that this PAC1944X opens the door for low voltage applications, specifically because we can measure the voltage rail with 16 bits of resolution from 0 to 9 volts. So why is 0 to 9 volts important? Well, a lithium-ion battery, a single cell, will go 0 to 4.5 volt max, and 0 to 9 volts is important for a dual cell battery application, right? So we've designed these PAC1944Xs to measure from 0 to 9 volts with 16 bits of precision on the voltage rail, and we then make it very friendly to applications like VR headsets or drones or smart city or video doorbell and security, for example. So we've done all that for the PAC1944X. And not only that, I would end on the fact that we've also allowed it to configure for 0 to 4.5 volts for those of you that are using single lithium-ion battery applications.
All right, great. So great overview. Let us go to the interwebs. Let's see who's out there and what questions we might have from our audience.
Okay.
Absolutely, Ross, and I'm sensing we do have a couple of questions. Our first one is via email, and that's going to read, how do you overcome placement and routing challenges when using up to 4 sense resistors?
Okay, this one's a good question, specifically because people that are routing their board or designing their system board, they get concerned about so many sense resistors grouped up in one part of the PCB. And so what the PAC1944X and 5X families has done well is our design allows for, well, first of all, it's a high impedance input type of design. And so what that does is it allows for longer traces on the board on your way to get to that sense resistor. So you don't need all the sense resistors designed on top of each other. They can be routed away, and in fact the datasheet allows for up to 1 kilo ohms of sense resistor trace resistance on the way to the IC itself.
Awesome. Well, thank you very much, Mitch. And we do have another question. This one's coming from LinkedIn from Roberto Iglesias. And it reads, hi, can you please let us know the lowest voltage and current that these devices can sense, as well as the minimum power that can be calculated and the time that it takes to have the data available?
Ah, that's a mouthful. Okay, so let's see if I can take it one at a time. So the lowest voltage, these devices are definitely good for your graphics boards. So when we talk about low voltage, I am thinking about things such as graphics chips or data centers, and we're good for that. So definitely lower than 1 volt is capable. And so another thing that when we think about lower voltage is, well, what's my accuracy of measurement on lower voltages? So for a current sense voltage, I can get to 0.1% accuracy for a range of 10 millivolts to 100 millivolts. And if I want to get even tighter measurement on my sense voltage, I'm going to be able to get to 1% accuracy on the current sense measurement for a 1 to 0.1 millivolt range. I think that's some of the answer to that question. So you also asked about lowest voltage. I think I answered essentially the range there. Take a look at our data sheet. We've got great graphs associated with the type of accuracy that you'll get, and we can go all the way down to 0, which is kind of it's fictitious, but we can go down lower and be able to be actively measured.
Thank you very much, Mitch. And we'll make sure to have any key links listed below in the description for our viewers to access those data sheets that you had mentioned. And also for Roberto, if you'd like to gain further clarification on your question, make sure to just send us an email at livestream@microchip.com. So we do have several questions. We appreciate the engagement from our audience. The next is going to be from Michael Pierce on YouTube. And Michael asked, do you have a part that is suitable for PoE applications that operate up to approximately 60 volts?
Okay, great question. In this case, we don't have one that goes up to 60 volts, but one of the things that our dual channel and single channel versions of this family can do is you can design off of a floating voltage node as long as the voltage remains under 40 volts. So what that can do is we can get closer to your 60 volt goal, and you can use a resistor divider, and as long as you're not exceeding 40 volts, we can get you a band of measurement with that resistor divider setup. We do have roadmaps that are going to go to higher voltages, but right now for this particular family and our family at Microchip, it's 0 to 40 volts.
Well, thank you again, Mitch, and we're just going to keep them coming right at you. The next one's coming from LinkedIn from Gherkin Tosin, and it reads, "Hi all, is it possible to configure the threshold values of the alerts?"
Great question. So what is really nice about the alerts is its flexible ability to adjust the limits, right? So I can use all 16 bits of a alert limiting capability to set it up. So basically, I have a register, limit register, that I can configure, and it has 16 bits of resolution, much like I have 16 bits of measurement on the voltage or the current. So the answer here is yes, and I have 16 bits of resolution with which to specifically set limits associated with the measurement of current, voltage, under current events and under voltage events. And also we have a wider limit setting register associated with power events. So that register is actually much bigger than 16 bits.
Perfect. Okay, well, thank you very much, Mitch, for taking the time to answer our audience questions. And to our audience, remember to check out our description below for some useful links that we had mentioned. And if we didn't have a chance to respond to your question today, make sure to send an email once more to livestream@microchip.com, and we'll get back to you as soon as possible. And lastly, I do want to remind everybody to please go ahead and follow us on LinkedIn and YouTube and subscribe to be the first to know about industry trends and hear from our experts here at Microchip. Back to you, Ross.
Great, thanks, and lots of great questions today. Lots of great interaction. So congratulations. That's fantastic.
Thanks.
So that kind of brings us to the end of this particular episode. Remember, if you want to watch this episode again or others, you can find that information at microchip.com/coffee break. This is season 5, episode 2. All of the previous 4 seasons are up there as well. So as I always encourage, go take a look if you haven't. Lots and lots of great information there. In 2 weeks, so that brings us to the end of today. In 2 weeks, our topic is silicon carbide and digital gate drivers, I believe, or something to that effect. I'll study up between now and then. In the meantime, thank yous. Thank you, Mitch, for coming in. Thanks, David, Sean, for all of the studio work. Thanks, Claudia, for keeping everything rolling and all of the details attended to. Thanks to Austin for fielding the questions and keeping things moving here in the studio. And I believe that is the end of today's show, and we will see you all in 2 weeks. Thanks very much.